team. I'm Kimberly. This is Hamza, Shiv, Gabe, Trevor, and Eli. Does anybody know where this fountain is? Yes, many of you have probably seen it. It's outside the Bellagio Hotel in Las Vegas, and it was created by WET. What makes their water fountain so special is they become water features. So they synchronize them to music, they add in light shows and special effects like fire, for example. Our goal is to scale down this experience and make it accessible in people's homes. So in this case, this would be scaled down into a light show. So just like you would go to a museum to see art or you watch Intel's drone shows, here you would get a light show with these little pods. On the right, or on the left, you see a concept drawing of what one of these pods would look like. And on the right is a concept drawing of how they would look like when they're swimming around in people's pools to a specified choreography. So we're basically making floating robots. They are wirelessly connected light pods that move in a choreographed sequence, and they are controlled by a central hub unit. So we just started off with the concept drawings that we showed you earlier, and this whole design process was guided by a lot of constraints, which are listed here. Like the pods need to move at more than 6 inches per second. They need to be charged and be controlled wirelessly. Their choreography takes place in a 15 by 15 foot area. The LEDs on top of the pods need to be visible from 50 feet away, and the diameter of the pods needs to be around 2.5 inches. So this is our system overview and how we design the system. On the left is the pod. Again, these are the little robots that are moving around that have the LEDs on top. And on the right is the hub, which is the central unit that controls all of the pods. So first, let's dive into the mechanical design. So on the left, you can see the SolidWorks model of the pod casing. It was built in 3 different sections, which are then assembled together, as you can see on the right. It's 3D printed, and it's important to note that this top part right here is printed in a transparent material. This is important when you remember the constraint that the LEDs need to be visible from 50 feet away. That's because we're using a visual tracking system, and having this dome diffuses the light, and it's easier for the system to pick up the pods. Then we also have inboard motor channels on either side. The pods will be swimming around in people's pools, so we don't want anything or anyone to get caught up in them. And then we also have these circular grooves. The pods will be docking and charging wirelessly on the hub, so we don't want the magnet or the charger to move around. We want those to stay secure. Then we have this O-ring groove right here. So when you're assembling the top and the middle section, we have an O-ring for waterproofing, and then a set of screws on the circumference to compress the O-ring. This hollow section in the middle contains the motherboard and the LED board, and then this hollow section right here contains the battery. We wanted to make sure that the heaviest section of the pod battery was at the bottom to center the pod, and so it wouldn't tilt on the side, which is why it's in the middle. Then we have 4 supports, which you can't see, but they're in the middle section of the pod here. These secure the motherboard and the LED board so they don't move around, and it helps with heat dissipation. We overlap this section on top of this section when we're assembling the middle and top parts. We marine epoxy it so it stays waterproof. And then these 4 supports right here go into these 4 grooves right here. This just increases the overall structural integrity of the pod. So we also don't want to build submarines. We want to make sure that the pods actually float for the choreography. So we check the balances of buoyancy and gravity. Just with rough calculations, we confirmed that the pod floats, and this was confirmed again when we've been doing testing and experimenting.
So the electronics on the pod are guided by the functions that they need to accomplish. So they need to be able to wirelessly communicate with the central hub unit, and that's being done using Bluetooth Low Energy, because that meets the space constraints and is also very low power consumption. We need to measure the orientation of the pod to aid with the localization system, and this is done using an onboard initial measurement unit. The pod electronics need to handle a lot of current. The LEDs draw about 4 amps of current, and the motors draw 1.5 amps, and that's a lot of current going through this that they need to handle. And finally, all of this needs to fit in a very small electrical package, and we're doing that using printed circuit boards. So our layout right now for the circuit boards is we have a 2-board stack where there's a motherboard which has most of the circuitry, and this implements all of the requirements that we're doing, and there's an LED daughter board that plugs in on top of this motherboard, which houses the LEDs. So that's the motherboard, which is being passed around, okay? And so there's an IMU on there, a Bluetooth chip, which is also the microcontroller, which is the sort of brains of this motherboard. There's a battery manager circuitry, which is a fuel gauge to monitor the current, monitor the battery, and also a battery charger to charge it. And it has 2 H bridges to power the motors. And there's some cool tricks on this motherboard. For instance, we have an onboard antenna, and this is for the Bluetooth communication, so 2.4 gigahertz send receive. There's a power plane, and this essentially handles all the high current that goes to the LEDs and the motors. And all of this high power circuitry needs to be kept away from the IMU, because the IMU has a magnetometer, and we don't want the high current here to affect the magnetometer there, so it's been placed far away from there.
All right, so as Hamza mentioned, we have an LED daughter board that basically houses the LEDs and kind of receives the control signals from the motherboard. So one of the main challenges that we faced while designing this was we wanted to ensure a constant brightness of the LEDs over the course of a light show. So if the voltage from the battery decreased over time, we want to still ensure that the LEDs were as bright. And since these LEDs can draw up to an amp at peak current usage, we need to make sure we can manage that current and also the heat that it generates. And since we have an IMU that sits directly beneath the LED board, we wanted to make sure that the magnetic interference is reduced. So a simple way to control an LED circuit would be to turn on and off a switch fast enough that your eye can't perceive the blinking. And the percentage of time that the switch is on will determine the brightness of the LEDs. But the problem with this is that over time, as your battery supply, or VDD in this case, decreases, the brightness of the LEDs will also decrease. So to solve this problem, we implemented a closed-loop current controller using an op-amp and a P-channel MOSFET. So what the op-amp does here is it ensures that the inputs are kept the same and that the voltage across this resistor is kept to be the same as the input through negative feedback. So over time, if the voltage from the battery decreases, the op-amp will adjust its output so that the voltage across this resistor is kept constant. And what that means is the current through the circuit is kept constant, and then if the current through the circuit is kept constant, the brightness of the LEDs are kept constant. So we implemented the circuit in 4 instances on a printed circuit board. So on the left here, you can see a power plane that wraps around the edge of the board. That's to make sure we can handle the 4 amps of current at peak usage. And also, we have a keep out zone that's here. So the IMU sits directly beneath this board. So we want to make sure that there's no current traces that run over the IMU and cause magnetic interference. Since we draw a lot of current, we also have heat, so we want to be able to manage that heat. So we implemented a thermal via pattern recommended by the manufacturers of the LED. So thermal vias are basically holes that are plated that provide a conduction path for the heat from the top to the bottom of the board. So on the bottom of the board, we have a large ground copper layer that helps spread out the heat and dissipate it. And we also have the spot for a heat sink that we can attach.
Now I'll talk about the hub design and the considerations that went into creating this. The hub is composed of 2 components, the actual processing unit and the dock. Beginning with the actual processing unit, it's composed of 3 components. The Intel NUC, which is a small but very powerful computer that runs on Linux, 2 NRF BLE master microcontrollers, and it only gets that communicate with the Intel NUC via serial communication. And this is done just with a simple micro USB cable, and then a power source. Now, you can consider this kind of like the brains of the entire operation. The Intel NUC contains all the code that runs the controls for the entire system. So it sends commands over to the BLE master, which are then sent to each pod via Bluetooth. And then there's the dock, which contains an electromagnet and an inductive coil. Now the purpose of this project is for the pods to go swimming and not for us to go swimming. So Essentially, what we really wanted to do was have the pods charge by themselves and dock by themselves. So over here on the left, you can see what we wanted the dock to actually do, which is kind of like pull the pods kind of closer to it with the electromagnet, have the inductive coils in the dock line up with the inductive coil on the pod, and then have that done all by itself. So over here, you can see that this LED has turned on, meaning that the inductive coils have lined up and the charging is actually happening. And over here on the right, you can see what we actually created. The main constraint here was waterproofing, because this thing's entirely submerged underwater. So this was easily solved with like just epoxying and having a wire penetrator, so that we could access the inductive coil and the electromagnet.
Okay, cool. So now that we've introduced you to all of the hardware, both electrical and mechanical in our project, it's time to tie it together in firmware and software. So everything that we've built works by intaking camera data and a desired pattern. From there, it'll tell the pods where to go, it'll tell which pod to turn on which LED and all that. So we might have our controls algorithms feeding over Bluetooth to all of our pods, which are floating out in the water. A little more complicated than that. We start on the dock, which is where all of our controls live, and from there we generate commands which will go out to each pod. We send those out over our PySerial micro USB cable, and we then have our masters send out those commands to all of our pods. All of our BLE masters, Bluetooth Low Energy masters, are running a multi-link version of NUS. NUS is the Nordic UART service, and basically it's a way for us to send command strings from our control loop all the way down to our peripherals. The multi-link aspect just means that we have one master able to drive to 4 peripherals, and so that means we have a scalable system that we can increase to as many peripherals as we want. On the pod side, once we've received a command, we write out a PWM value to our lights, or our LEDs and our motors, and that way we can drive them at varying speeds and brightness. We communicate over I2C with our batteries, so we can tell if we have to go charge at the inductive charging station. And then we also grab heading over I2C from IMU so that we can drive our pods in the correct orientation.
Okay, so before we can tell the pods where to go, we need to know where they currently are. So we looked at a couple different options for localization systems and ultimately settled on using an overhead mounted camera for ease of use and portability. It uses OpenCV, which is an open source library of image processing algorithms, and it relies heavily on a color filter. Conveniently, our pods light up brightly in whatever color we tell them to, so a color filter is a good solution for this problem. We also don't want the camera to be directly mounted overhead and being on top of the pool or something weird, so it has to be off to the side. What this means is that what the camera actually sees, the XY position on the screen, doesn't necessarily correspond to the XY position on the ground. So we have to apply a process called a homographic transformation, which is where you take one plane and project it onto another. This is done by multiplying the coordinates by a matrix, which is calculated in the calibration process, which you only have to do once when you're setting up, and then the system can run without doing it again. We also added a couple features that we call a smart filter that helps reduce false detections such as ripples off of the water. It helps it figure out which pod is which by keeping track of pod movement, rather because all the pods look exactly the same. You can't just tell them apart just by looking at them. So in order to test this, rather than working with pods, we took one of the LED boards that we had and put a dome on top of it, strapped it on top of a remote control car, and drove it around the Parsons patio. So here you can see it driving around. Our requirements were 15 by 50 foot performance space, which we were able to do. We also needed to have a 4-inch position resolution, which it beat, as well as a 6 inches per second tracking speed, which it also beat. So next, we started working on the controls. We also didn't wanted to work on this while we were also working on the pods. So instead of tracking pods, we tracked little green pieces of fabric attached to wires. And what happens when you track them is it looks like this. So this is the output of the controller. Each green dot represents one of the pods or objects that's being tracked or controlled. It has a static number so that you can send it commands and keep track of which is which. It has heading information, which is the white arrow. And then the pink X's are where each pod is being told to go. And the pink arrows are the control signals that they need to follow. You'll notice they're not doing a very good job following the points. This is because we're moving them around by hand and we're not very good at tracking points. So the actual controller, when you integrate this with the Bluetooth, uses a PD controller. It takes the XY position from the camera, which can't determine the orientation, so it gets the orientation from the IMU on each pod, and takes those together to compute the control signals. It Then it uses another piece of software called the trajectory planner, which makes the different patterns and shapes that we want to draw. It also keeps track of what speed to move the points, if all the pods are close to their targets, changing points, assigning each pod to a different point, and stuff like that. So we wanted to test this in a simulation. So here we have the pods fully simulated. We start with 5 pods and we tell them to start moving in a circle. So it creates the circle, assigns each pod to a point, and then starts moving. It works dynamically with any number of pods, so we add in a new pod and it adjusts the pattern accordingly. And it can also change between different patterns. So here it's changing from a circle to a figure 8 with minimal disruption. And now the moment that you've all been waiting for, when we integrate everything together and it works perfectly on the first try. So here's our final product. The video sped up a little bit for time. This shows 2 pods moving in a circle. This is with the overhead mounted camera tracking their position, the IMU sending back their orientation, and all the systems working together. And it moves in a circle. So lastly, we want to thank all the people who helped us with this project. We couldn't have done it without all the people at WET, our great liaisons, a lot of staff and faculty who helped us out here, as well as our fall juniors who helped us lay the groundwork for this project. And with that, we'll take any questions that you might have.
How do you guys make sure they don't collide with each other?
Right now, it hasn't been an issue because we don't have a whole lot of pods in a small amount of space. The trajectory planner generally puts them pretty far apart from each other, so it hasn't been an issue so far.
Did you make a PE controller?
So yeah, we started off with just a proportional controller, but we noticed a lot of overshoot. So we added the derivative action to kind of account for that overshoot and correct for that, and it worked well for us for our purposes. We just went with that.
It kind of seems like you're intending for the pods to stay in like commercial pools for a long time. Did you consider like the effects of chlorine on the material over time?
So for the motors, right now we haven't done anything to prevent corrosion, but we know like if we apply a layer of wax, it'll help. For the O-rings, also we selected a material that does well in chlorinated water.
What did you say the accuracy of the tracking system was?
So from the demo we had running for a 15 by 15 foot area, it had a 4-inch position resolution and could track objects moving greater than 6 inches per second.
So is that 4 inches enough to get it back to the dock for the charger?
We didn't actually get to try driving them back with the control system to the dock, so I can't really say.
But the magnet from the GIF, it pulls
Big
it from
magnet
like,
to pull it.
from like around, so it doesn't have to be precise.
Have you tested your tracking of them in different lighting conditions?
Yeah, we've done it in a couple different lighting conditions, one basement and another basement. It does have some issues with bright sunlight. The color filter can be adjusted to help reduce that. It's a little kind of, you have to play with it depending on what environment you're in.
Does WET have a cost goal for this system? Like, we want to go to the store and buy one, what would it cost me?
For this project, we didn't have any cost constraints. No. Any other questions?
Yeah. So I'm wondering, if one pods are moving like there's some waves or something, like have you tested the robustness against wind or wave? You know, like when a lot of them start moving around, will they start diverging, you know, the control a bit?
The pods themselves won't really interfere with others. Like when we swim them around in a water tank, like you don't really see any ripples on the water. It's really slow. I don't know if you can see it in the video.
We haven't tested the system outside the basement.
Yeah.
Our controller is for like still water. We haven't really gone into choppy water, given that they're going to be in pools.
Even if you're in pools, you still have like birds and other stuff like that, right? So wind, birds will still be there.
Yeah.
When we were designing for still water because we knew that that's going to be hard.
Why do you use I/C for fluid?
So the battery. So first semester we picked a battery management chip, which is on a SparkOne breakout board, and then the chip has accuracy, so we just talked to that accuracy.
What's the battery life when you're running this? How
So
long?
the battery is 6,000 milliamp hours, and so at full peak, like operating, it will last about 40 minutes for 40 minutes to an hour. But we never actually reach full peak usage, and in our when we've been using it, it lasts about 5 to 6 hours.
Was there any point during the project process that there was a huge challenge that needed to create a pivot in the direction of something?
No pivot, like we ended up doing what we were planning on. I guess the hardest part was integrating all the systems because everyone was working on like electrical, mechanical, visualization, localization systems. So hardest part was integrating everything.
Initially, in the first semester, we were looking at sonar for tracking, but that was a lot of work, including like the system we already had to do, and so that's why we just went on the reliable visual tracking system.
Like Eli said, we were using a PD controller, but we were initially using a P controller, but the overshoot was too much, so.
For the hub, I saw that you only had plans for like maybe 1 or 2 things. Do you plan to have a hub large enough to charge all of them at the same time?
Yeah, I think the idea is to have like multiple docks.
Eventually, as a product, it will be a custom deck which will have all the pods already. You just put the deck down, and the pods will like deploy with the show.
When did you guys actually get this into the water, and what did you learn when you actually got it into the water and started trying things?
That video was 2 days ago. We started water testing actually a while ago. I don't remember exactly.
I think we've had a kiddie pool for testing for like almost the entire year. We've been testing all our things in water. The actual final control we I think started like 4 weeks ago in the water we put the pod in.
Yes.
Yeah.
Probably the most interesting part there was the hydrodynamics of our robot are really weird.
And accounting for like the torques and the drag and stuff was really hard.
And just it drifting off in the water.
How do you plan on draining that kiddie pool you've now filled up in the clinic space?
We're looking for volunteers now.
We'll pass on a sign-up sheet.
Do you know what's going to happen to this project after you guys are done?
What's going to continue working on it to make it suitable for the market?
What do you have any theories of what is causing the knots exactly?
Yeah, so what's going on here is that the motors are actually pretty imbalanced on the pod, so one ends up moving faster than the other. So it gets to the point that it needs to before the other one does. But based on the way we have the trajectory planner set up at this time, it didn't advance the points yet. So it ends up getting to the point and kind of just like diddling around it while the other one is still waiting there. And once it does get to it, then they start moving. So you see it's acting a little weird, and then it goes to the next place, acts a little weird again, and goes to the next place.
So in that case, you're using a discrete point model rather than like a continuous trajectory?
Yeah, it's adjustable, so we can set it to just like a couple points around a circle or many points around a circle. We found that actually a lower number of points corresponded to smoother movement.
Okay, thank you.
This is gonna suck.